In this video, we're going to look at a few more examples of the alternating series test. Test the following series for convergence or divergence. Question A, summation n equals 2 to infinity, negative 1 to the power of n times log n divided by n. Question B, summation n equals 1 to infinity, negative 1 to the power of n times n divided by 2n plus 5. Question C, summation n equals 1 to infinity, negative 1 to the power of n times log of e to the n divided by cos of n pi times n to the fourth. Let's look at question A first. Here we have summation n equals 2 to infinity, negative 1 to the power of n times log n divided by n. We need to check the two conditions of the alternating series test. Condition 1 means that the terms have to be decreasing. an plus 1 is less than an. Now it's not clear that the terms given by an equals log n divided by n are decreasing in magnitude. So let's consider the related function f of x is equal to log x divided by x, and let's use the derivative to find out whether the function is decreasing. So let's apply the quotient rule. F of x is equal to log x divided by x. We'll apply the quotient rule to find the derivative. F prime of x is equal to square the bottom, x squared. Take the bottom times the derivative of the top, and derivative of log x is equal to 1 over x, minus the top log x times the derivative of the bottom, which is x, and derivative of x is 1. So simplify, we get 1 minus log x divided by x squared. Now f prime of x is less than 0 when the numerator, 1 minus log x, is negative, because the denominator is always positive. X squared is always positive. So let's force the numerator to be negative and solve for x. Bring log x to the right-hand side. We get 1 is less than log x. Exponentiate both sides. We get e to the 1 is less than e to the log x. E and log cancel out. So we get x larger than e. So when x is larger than e, the function f of x is decreasing. That means when n is larger or equal to 3, the terms an is equal to log n divided by n are decreasing. So we have just shown that an plus 1 is less than an for n larger or equal to 3. Now we need to look at the second condition, and the second condition is that the limit of the nth term has to be 0 as n goes to infinity. Limit n goes to infinity of an is equal to 0. So we have the limit as n goes to infinity of log n divided by n. Now if you plug in infinity, you will see that this has the infinity divided by infinity pattern. That means we have to apply L'Hopital's rule to solve for this limit. So limit as n approaches infinity of log n divided by n is equal to, let's put h here to symbolize that we're applying L'Hopital's rule. Limit n approaches infinity, differentiate the numerator, derivative of log x is equal to 1 over x, so derivative of log n is equal to 1 divided by n. Derivative of the denominator, derivative of n is equal to 1. Take the limit, 1 over infinity, that's equal to 0. So both conditions of the alternating series test have been satisfied. Condition 1. Condition 1 is that the terms are decreasing in magnitude. An plus 1 is less than an. We apply the derivative to prove that. Condition 2, the limit as n approaches infinity of an has to be equal to 0, and we applied the L'Hopital's rule to prove that. Since both conditions are satisfied, the given series, summation n equals 2 to infinity minus 1 to the power of n times log n divided by n converges by the alternating series test. We will abbreviate that, converges by AST, alternating series test. All right, let's look at the second example. Here we have summation n equals 1 to infinity minus 1 to the power of n times n divided by 2n plus 5. Now this series is definitely alternating because it has the factor negative 1 to the power of n. But let's look at the limit of the nth term. Let's look at the limit as n approaches infinity of n divided by 2n plus 5. This is equal to limit n approaches infinity. Let's divide by the highest power in the denominator. So we divide by n, divide by n, and divide by n, and take the limit. We have limit n approaches infinity. N divided by n, that gives us 1. 2n divided by n, the n's cancel out. We get 2 plus 5 over n. Now 5 over n approaches 0 as n approaches infinity. So the limit of the nth term is equal to a half. And of course that means it diverges by the divergence test. Now let's explore this a little bit further. Let's look at the limit as n approaches infinity of minus 1 to the power of n times n divided by 2n plus 5. Now notice that when n is even, and even integers, for example 2, 4, or 6, then the limit will be 1/2. But when n is an odd integer, for example 1, 3, 5, and so on, the limit as n goes to infinity will be negative 1/2. In either case, the limit as n approaches infinity of negative 1 to the power of n times n divided by 2n plus 5 does not equal to 0. That means the series diverges by the divergence test. So this series diverges. Even though it's an alternating series, because the limit as n approaches infinity of an, the limit of the nth term, is not 0, the series diverges by the divergent test. I should say divergence. Let me correct that. Divergence test. All right. Let's look at question C. Here we have summation negative 1 to the n, log of e to the n, divided by cos of n pi times n to the 4th. Well, it's kind of a loaded question, so we do need to simplify the general term first. Let's look at log of e to the n. Log of e to the n, log cancels e, and we just get n. Now, let's look at cos of n pi. Let's look at the sequence cos of n pi when n ranges from 1 to infinity. Let's put this in brackets, cos of n pi. Now, plug in n equals 1, we get cosine of pi. Plug n equals 2, we get cos of 2 pi. Plug n equals 3, we get cos of 3 pi. N equals 4, we get cos of 4 pi, and so on. Now, what is cos of pi? Cos of pi, cos of 180 degrees, that's negative 1. Cos of 2 pi, cos of 360 degrees, that's 1. Cos of 3 pi is negative 1. Cos of 4 pi, cos of any even multiple of pi would be 1, and cosine of any odd multiple of pi would be negative 1. So now, let's look at negative 1 to the power of n. Let's look at the sequence. N goes from 1 to infinity. Plug in n equals 1, we get negative 1 to the power of 1, that's negative 1. Negative 1 squared, negative 1 raised to an even power will be plus 1, and it's just going to alternate. Negative 1, 1, negative 1, 1, negative 1, 1. It alternates exactly the same way as cos of n pi. In fact, if you look at these two sequences, you will realize that negative 1 to the n is equal to cosine of n pi. That means these two terms can cancel out. All right, let's simplify a bit further. So we have summation n equals 1 to infinity, negative 1 to the n, times log of e to the n, divided by cos of n pi times n to the 4th. Now, we showed that negative 1 to the n is exactly the same as cos of n pi. We also showed that log of e to the n is equal to n. So when we simplify this, we get summation n equals 1 to infinity, n divided by n to the 4th. This is equal to summation n equals 1 to infinity, 1 divided by n cubed. So after simplification, we realize that the given series is not an alternating series. So not an alternating series. Even though it looked like an alternating series, but it's not, because cos of n pi cancels with negative 1 to the n. In fact, the given series, summation n equals 1 to infinity minus 1 to the n log of e to the n divided by cos of n pi times n to the fourth. After simplification, this is equal to summation n equals 1 to infinity 1 over n cubed, which is in fact a p-series with p equals 3. P-series, p is equal to 3, and p is larger than 1, 3 is bigger than 1, so the given series converges because it's a p-series with p equals 3 larger than 1. So the given series converges because it's a p-series with p equals 3 greater than 1. So this was kind of a tricky question because it actually wasn't an alternating series at all after we simplified it, and we realized that it is just a p-series, and summation 1 over n cubed is a convergent p-series because the value of p is equal to 3, which is greater than 1. All right, thanks.